In this video we are continuing with exponentials and logarithms b, and we're going to solve equations with unknown exponents. So if an unknown value is the exponent of a term, for example 10 to the power x or e to the power x, we're able to solve for x by taking the logarithm of both sides of that equation. Now, we will obtain the same solution using any base for our logarithm, but generally our calculators will only work for base 10 or base e, which is the natural logarithm, as we learned before. So let's have a look at example 1. We want to solve e to the power x equals 7. So we can firstly see we've got e to the power x equals 7, and obviously there's no way of knowing, like just offhand, if it was 2 to the power x equals 4, we would know that 2 squared is 4, and we would know that x is 2. But unfortunately here there's no way of telling what that is. So what we need to do, like I've already said, is take the logarithms of each side of the equation. Okay, so I'll take the natural logarithm, obviously because I'm working with the exponential here, the exponential constant. So I've got the natural logarithm of e to the x equals the natural logarithm of 7. Now that natural logarithm of e to the x, remember that's equal to log to the base e of e to the x, which obviously I can bring my power down to act as a multiplier for the logarithm. So that's x times log to the base e of e. Now log to the base e of e is 1, as we've previously worked with, so I'm just left with x here. So the left hand side of my equation, I'm left with x, which is what I want, and the right hand side of the equation is the natural logarithm of 7. I can then use my calculator, natural logarithm of 7, so x is equal to 1.946 to 3 decimal places. So just now would be a good time to pause the video and come back for example 2. Welcome back folks, so hopefully you've copied down example 1, because I told you to pause the video and come back for example 2, and not actually to copy down example 1 if you haven't done that already. So example 2, we want to solve 7 to the power y equals 9. So again, like we learned in the last example, we need to take the logarithms of each side of the equation. So this time, I'm going to take log to the base 10 of each side of the equation. So that gives me log to the base 10 of 7 to the power y equals log to the base 10 of 9. Now, remember my property of logarithms, if my argument has a power, that power can become a multiplier of the logarithm itself. So that's going to be y times log to the base 10 of 7, and that's still equal to log to the base 10 of 9. Now I want y to be the subject of my formula, but it's currently being multiplied by log to the base 10 of 7. So I need to divide throughout by log to the base 10 of 7, which gives me y equals log to the base 10 of 9 over log to the base 10 of 7. And I need to put that into my calculator in its entirety. I can't simplify that in any way. Some people might think you can divide the arguments here, but remember that's if you're it's the difference of terms when you do that. So log to the base 10 of 9 over log to the base 10 of 7, and that gives us a value for y, 1.129 to 3 decimal places. So once again folks, it would be a good idea to pause the video, take this example down in your notes, and then come back for example 3. Okay folks, and the last one here, this time we want to solve 5 to the power 3x plus 1 equals 40. So you can see in this example this time that there's a lot more going on in the power. Previously we only had the variable as the power, but this time we've got the variable, it's multiplied by 3, and then there's a 1 added on to that. Okay, so if we take the logarithms of both sides, whether that's a natural logarithm or log to the base 10, it doesn't matter, you'll still get the same final answer. So we've got log to the base 10 of 5 to the power 3x plus 1 equals log to the base 10 of 40. Remember, 3x plus 1 is the power of the argument, so it can become the multiplier of log to the base 10 of 5, like so. Now the 3x plus 1 is currently being multiplied by log to the base 10 of 5, so I need to divide throughout by log to the base 10 of 5. And I can try and evaluate the right hand side of my calculator, so log to the base 10 of 40 over log to the base 10 of 5 is 2.292. Now I would keep that answer in your calculator because we want to be as accurate as possible with our final answer. Okay, so keeping that 2.292 and all the other decimal places that your calculator currently says, subtracting 1 from that gives us 1.292. Keep that in your calculator as well, so we've got accuracy as far as we can, and divide throughout by 3, I get 0.431 to 3 decimal places, so I can round it at that point. So don't round up here, because it could mean that your final answer is wrong if you round too early. So folks, that's the end of example 3, so it would be a good idea to pause the video before the screen goes blank, and copy this down in your notes if you haven't already, and then complete the assigned exercise for today.